Good morning, friends. This is Dr. Rajkumar, Professor Mechanical. This is the second video what we are posting in Thermal Engineering 1, right? So in the first video, we had a discussion on thermal efficiency of an Otto cycle, right? We have derived expression for thermal efficiency of the Otto cycle. In this video, we will be discussing about mean effective pressure of an Otto cycle, right? So generally people will think that mean effective pressure means we are going to measure the pressure inside the cylinder and you are going to take average of that. So whereas in this case it is not possible, right? So this is not the pressure what we are measuring in IC engine, right? This is one of the performance parameter. Say for example, thermal efficiency, mean effective pressure, cylinder pressure and exhaust gas temperature, this all comes under performance parameter. Likewise, this cylinder pressure, that is mean effective pressure, will be the one of the performance parameter for measuring performance of an internal combustion engine. Coming to, so another some of the parameters also there. Combustion parameters are there, exhaust parameters are there. Combustion parameters, say for example heat release rate and ignition delay, these two are comes under combustion parameter. Then coming to exhaust parameter, exhaust gas parameters, carbon dioxide, carbon monoxide, sulfur oxide, NOx, water vapor and so on, right? So in this what we are going to discuss now is, as I said already, mean effective pressure of an Otto cycle, right? So this mean effective pressure varies with respect to compression ratio and expansion ratio and initial pressure. These are all the factors will be given while solving problems. So I am going to derive the expression for mean effective pressure now. Let me start with the PV and TS diagram. So always you should remember this PV and TS diagram, right, of the Otto cycle. So simple methodology, as we have discussed in the first video, two vertical lines and you are connecting these two. Likewise, you are connecting these two. Then mirror image of that video. This is state 1, 2 and 3, 4. 1, 2, 3, 4, right? So this is your PV diagram. This is your TS diagram. So what is mean effective pressure, right? Mean effective pressure is work done by stroke volume. So first I am going to calculate the value of work done for this particular process, right? Work done. So strictly speaking, so we are in need of work done for the process 1, 2, 3, 4, 1, right? So a concept is there. Area under the curve in PV diagram will provide the value of work done. What is that? Area under the curve in PV diagram will provide the value of work done. Say for example, let me share this small PV diagram. This is 1 to 2. This is PV. You all know that work done for this particular constant pressure process will be integral P dV. So this P can be taken outside. Then integral of dV will provide V within 1 to 2. So this will become PV2 minus PV1. PV2 minus PV1. As I said before, area under the curve in PV diagram will provide the value of work done, right? So this is the process 1 to 2. As I said before, constant pressure process mathematically can be expressed as integral of P dV. P is a constant, that's why I am taking outside. While you are integrating V, you will get V upper limit 2, lower limit 1. So finally this will become PV2 minus PV1 mathematically, right? This can be proved with this diagram. So this is the required area, right? This is the required area. What I am hatching now? Height is P1, which is equal to P2, which is equal to P. This width is required now, right? So up to this is V1. From this place to this place, this is V2. So we are in need of this portion, right? So V2 minus V1 will provide this portion, right? Now height P1 or P2 or P into V2 minus V1 will provide the value of work done, right? Likewise, we are going to calculate for this particular process. So for to find the value of work done, I am in need of this area. I am in need of this area. What I am going to do now is, I wanted to calculate the work done for the process 3 to 4 isentropic minus work done for the process of 1 to 2 isentropic, right? Say for example, area so here let it be A comma B, right? So to find the value of work done, area AB 34A minus AB 21A. I think you will understand, right? So let me hatch all those things. So what I am doing now is, I am going to subtract this green color area from this red color, right? So this total portion will give you the value of work done for the process 3 to 4. This portion alone will give you the value of work done for this 1 to 2. We are in need of this portion, right? So from thermodynamics you might have studied the value of work done for isentropic process is 1 by gamma minus 1 multiplied by P3 V3 minus P4 V4 minus of 1 by gamma minus 1 multiplied with P2 V2 minus P1 V1. What I am doing now is, I am taking this 1 by gamma minus 1 as a common factor outside. So 1 by gamma minus 1 whole multiplied with P3 V3 minus P4 V4 minus of P2 V2 minus P1 V1, right? Here what we are doing is, while deriving this equation, we are assuming that clearance volume is unity. Clearance volume is 1, Vc or V2 or V3. So here all are same. So this is your clearance volume. Alright, this is your clearance volume. So all these things are same. Vc, V2, V3, right? So we are assuming that clearance volume is 1 or unity. So in the next step, 1 by gamma minus 1 multiplied with V3 I am taking outside from these two factors. V3 can be taken outside. P3 minus P4 into V4 by V3 minus, from here I can take V2 outside. V2 multiplied with P2 minus P1 into V1 by V2, right? In the next step, I am leaving these two, V2 and, because which is equal to 1. I am leaving these two factor because V2 equal to V1 equal to, this will become 1, which is equal to 1 because it is a clearance volume. So we have assumed that clearance volume is 1. So that's why I am eliminating these two factors, right? Then what happened to the rest of the parameters? 1 by gamma minus 1 multiplied with P3 minus P4 into V4 by V3. What is V4 by V3? We have discussed in the previous video. V4 by V3, V1 by V2 is equal to R, known as compression ratio. This is your V1, right? This is your V1. So this is your V2, right? From this place to this place, this is V2. Here this is V1. V1 by V2 is nothing but V2, I can write over here, right? V1 by V2 is nothing but compression ratio. V1 by V2, which is equal to V4 by V3. V4 by V3 is also equal to R, expansion ratio, right? Compression ratio, expansion ratio. So both are same in Otto cycle. So I am writing this V1 by V2 is equal to R, V4 by V3 is equal to R. This always you should remember, right? P4 multiplied with V4 by V3 is nothing but R minus of V2 we have eliminated already, P2 minus P1 R. So coming to this 1 minus gamma minus 1 by gamma minus 1 multiplied with, so what I am doing now is I am taking P4R from these two factors, right? P4R, so P3 by P4R will become at this place, right? Minus 1 minus of, from these two I am taking P1R outside, so you will get P2 by P1R minus 1. So for these two things, what I am doing is, you may be knowing that isentropic relations for PV is P2 by P1 is V1 by V2 to the power gamma. Likewise, P3 by P4, these are all isentropic relation of for the process 1 to 2 PV relation. You might have studied in thermodynamics, right? This is PV relation for the process 1 to 2, particularly isentropic process, right? Likewise, P3 by P4 is also isentropic process. P3 by P4 is V4 by V3 to the power gamma. V1 by V2 is nothing but compression ratio. So P2 can be written as R power gamma. Likewise, P3 can be written as R power gamma into P1. P3 can be written as P4 into R power gamma. So these two things you should remember. So when you are applying these two in this corresponding equation, you will get 1 by gamma minus 1 multiplied by, this is P4R will be as it is, multiplied with this P3 can be replaced with P4R power gamma. P4R power gamma, right? Minus P1R into P1R power gamma divided by P1R already there, minus 1. Again this equation will become like this. So I am taking R from these two as a common factor. So R will come outside, R by gamma minus 1 multiplied by r power gamma r power 1. So r power gamma minus 1 minus 1, right, minus of P1R P4R multiplied with r power gamma minus 1 minus 1 minus of P1R already we have taken outside. So minus P1 into this will become r power gamma minus 1 minus 1, right. So from these two factor I can take r power gamma minus 1 minus 1 as a common factor, right. So r by gamma minus 1 multiplied with r power gamma minus 1 minus 1 into P4 minus P1. So from these two factors, so from here I can take P1 as outside from this second factor. So finally this will become P1R divided by gamma minus 1 multiplied with r power gamma minus 1 minus 1 into P4 by P1 minus 1, right. So this P4 by P1 is termed as pressure ratio. P4 by pressure ratio K, let it be K. So V1 by V2 is compression ratio, V4 by V3 is also compression ratio. Likewise P4 by P1 is pressure ratio, let it be K, right. So finally the work done expression will become P1R divided by gamma minus 1 multiplied with r power gamma minus 1 minus 1 into K minus 1. So this is what the expression for work done allowed. So we have to calculate, see so far what we have discussed is work done. So then we should go for stroke volume. So what we are going to do now is, so we have to find the value of, to find the stroke volume, to find stroke volume. Stroke volume is nothing but total volume minus clearance only. V1 minus V2, this is the stroke volume, right. So this is TDC, this is BDC. The volume occupied in between TDC to BDC is known as stroke volume. Throughout this piston can travel up and down, right. So Vs is nothing but V1 minus V2, right. So from this I am taking V2 outside. So this will become V1 by V2 minus 1. So you know that V1 by V2 is nothing but compression ratio. So V1 by V2 is nothing but compression ratio. V2 is nothing but clearance volume, which is equal to 1. This is equal to R. So finally the expression will become like this. Vs is R minus 1. So final output will become like this. Mean effective pressure is equal to work done divided by stroke volume. So that is P1R multiplied with r power gamma minus 1 into K minus 1 divided by gamma minus 1 into r minus 1. So this is what the expression of a mean effective pressure. Expression of a mean effective pressure. So finally the expression for mean effective pressure will become like this: P1R into r power gamma minus 1 into K minus 1, gamma minus 1 into r minus 1. So now the mean effective pressure will vary with respect to, so you cannot measure the mean effective pressure inside the cylinder because it is not a constant. It varies with respect to several factors such as compression ratio, this is pressure ratio, and gamma, and so on, right. So hope you will understand. So let me conclude with this. Thank you for watching.